discussing implementation of quantum computing, but in this particular week we are focusing more on the basics in relation to the implementations that we have discussed over the last several weeks. The reason for making this revision is to make an understanding of all the connects that exist between the basics as well as the implementation angles. So, in this regard, let us once more revisit the concept of the bit and the qubit as to how we can look at it. In some sense, a classical bit has exactly two possibilities, as we all know. On the other hand, the quantum bits, as we call about, are shown in terms of spheres. That is because there is a polarization vector which keeps on taking any particular position around the entire sphere. And so, this is represented in terms of the coefficients of each of these different directions that it leads to in terms of the possibilities of the two directions, and that is known as the density matrix. The equalities which exist in some sense are defined in regard to the bits to the qubits. When the density matrix is pointing toward upward direction, then it is, say, one particular state of the qubit which is equal to a particular measurement in terms of the bit. So, the zeros and ones in some sense represent the two opposite cases of the sphere points that we are looking at in terms of quantum. So, the density matrix essentially represents the probability of the state that we are finally measuring. So, when it is the 0th state, then it has a particular diagonal element only populated, whereas when it is the excised state, then it is the other diagonal element which is unity. So, for single qubit operations, there is a continuous sets of values. For a single qubit operation, therefore, there are many sets of values that the state, the density matrix can take as a function of time, for instance, as it is evolved with the help of the Schrodinger equation. So, this is the integrated part of the Schrodinger equation, where the Hamiltonian is thought to be constant over the short period of time that this integration, that this time evolution is occurring. So, the time evolution essentially occurs as a result of the unitary transforms provided by the Hamiltonian. So, this is the unitary operation we are looking at as the state is changing with time. Now, the curious aspect of the quantum computing lies in the fact that in terms of bits, the additions or the putting together of bits puts them in sense as it is shown here pictorially, and it can be always put together such that it can also be taken apart in the same way. So, that the left hand side and the right hand side for the classical case always remains the same. On the other hand, that is not quite true when we are looking at the putting together of quantum bits, because there the simple additive properties of these kinds are not going to work, and the cases where these connectivities of this kind work and you can always look at them together is the case where the qubit is assuming and taking all other possible states, as we discussed in the last slide, where the final measure of a particular value of the qubit is a representation of the probability of one particular state with respect to the other in terms of the classical sense. So, in some sense, the collapse of the wave function into one or the other is possible because of the spherical principle that we have developed, where we are saying that the all possible values can then be looked at as a function of the way at any point of time the measurement is looked at, and as a result what is happening is at any point of time the collapse leads to the values that are connected to this particular measure at that time. So, this is a probability or the principle of superposition of the particular aspect of being in one versus the other state. So, this is the principle of superposition whenever we talk about for the single qubit, which can exist in this kind of a form. However, when two qubits come together, the picture is not the same, because this does not give rise to a new set which can be broken down into this. So, this overall idea that the quantum states can always be separable. So, the separable part is always known as superposition conditions. So, there can be cases where the qubits come together, but they will only behave as additive properties, then they are going to remain as superposition states. However, if they cannot follow that principle and they are of the kind where we end up producing results where they cannot be looked at simple additive properties, then this is the idea of entanglement, and that is happening solely because of the process of tensor products that occur for quantum systems in between the matrices. So, these non-separable quantum states essentially give rise to conditions where they are not possible to be taken down to the original starting points of the qubits that these individuals can be related to, and therefore, their behavior is very different and not the kind of things that we are used to, and that is the idea about entanglement. In some sense, it also gives rise to this unique nature where the measurement of one of the parts of the entangled set gives rise to the measurement of the other entangled set. That is because they can only exist in a particular state and they cannot be separated out. So, even if they are physically separated, their behavior can be measured the moment and one of them is measured in this sense. So, entangled states behave in a very different way as compared to the regular bits in some sense, and that particular idea of entanglement is at the heart of quantum computing, and this has been a statement which has been made several times by me in this entire course to ensure that we realize the main aspect where the quantumness plays a very important role. So, let us see how we go ahead with this. So, the stability criteria which is often used for this is that the number of qubits, this is at the time when we were making sure that the implementation aspects are looked at properly. So, the machine should have a collection of bits and these bits would generally be of numbers which make some levels, say 1000 qubits or so. It should be possible to set all the memory bits to 0 before the start of each computation. The error rates should be sufficiently small, maybe less than 10 to the power -4 or so. It must be possible to perform elementary logic operations between pairs of bits, and reliable output of the final result should be possible. And so, this is basically the criteria which was initially taken from the principles which were developed earlier by DiVincenzo as we discussed, and most of the aspects of the work is done in terms of the unitary transforms which occur at the quantum level, but they can be controlled in terms of the unitary transfers or the data input output, because those are the points which relate to the outside world, and that is one thing which I think was also obvious when we were talking about the D-wave technology of implementation. So, here in real term of the physical realization of the qubit, here goes some of the ideas which have been discussed in detail. The ion trap and the neutral atoms, for instance, have the different states where these are under the different trapped conditions, and they correlate, and that is the ones which have been addressed. There have been other areas which are the photon based quantum computing, where the spins of the systems are being addressed by using the photon current going clockwise versus counterclockwise has produced the different results which have been utilized in terms of photon based quantum computing. And it has also utilized many other ways of looking at this problem. And the other very important implementation qubit has been the superconducting qubit, and that was partly one of the ones which was used in D-wave computing, where the qubits are superconducting loops which were addressed by using either the current loop going one way or the magnetic loop going the other way. And in case of D-wave, it was the current loop going clockwise versus counterclockwise, and the magnetic field created being of the two opposite kinds, which were utilized for developing the computer. The other important aspect is the Cooper pair box, where the spins of the system are being utilized, and there are a number of pairs which are being used. The number of pairs essentially ensure whether it is of one state versus the other. Similarly, they can be addressed by using the giant magnetic field principles of the SQUID, and we have discussed a little bit of it in terms of applying the current and seeing the magnetic field aspects as a result of these applications. So that is the place where spintronics was talked about. As we discussed in the last week. Semiconductor charge qubit was also the case where we used a single quantum dot, where the energy states of the quantum dots played a role. If double quantum dots were used, then they gave rise to 2 qubit conditions. The spin qubit has been very effective in terms of being either a nuclear spin, which has been addressed in terms of liquid state NMR as well as solid state NMR, or the electron spin, which have been utilized in many applications also. So, the major aspects of the quantum computing also lies in terms of the decoherence and the interaction with the macroscopic environment, because the essential quantum nature of the system diminishes after because there is a lifetime which the quantum system will be able to preserve its information, and that is the part which is important. So, if it is the Markov kind of a process, which is typical of the NMR spin cases, these are the T1, T2, these follow typical exponential decays, and there are the excited state time scales versus the phase of the system time scales, which have different time scales. Obviously, the phase across the different spins have a faster rate of decay compared to the electronic state decay. So, this corresponds to the electronic state or the particular nuclear state that has been looked at, spin state, whereas this one corresponds to the relative phase of the states that are being looked at, and so that has a faster rate compared to the other one. By respective, both of them correspond to the decoherence of the system, and there are also cases where the decoherence of the state could be non-exponential, and that is more to do with the electrons and other conditions. And so, depending on whether we are going to be having any of these particular states where we have created a superposition of the quantum information state, as we showed in the actual case. So, this is the quantum state, which is the having all the information. It actually goes down to the classical state, which is then has lost all the coherent aspects in it. And so, these are the major reasons why has to be careful in terms of making sure that we are able to measure before the interaction takes it down to the classical limit. So, the macroscopic environmental effects have to be reduced as much as possible. So, the one aspect which has been important in that sense has been the measure of decoherence, which is basis dependent and is additive for a few qubits, but is applicable for any time scales and complicated system dynamics. So, this is the kind of principle where the coherence of the system sort of diminishes, and that is one of the part which is important to make sure that it is not too small at any point of time, because interactions or carrying out gates would require the coherence to be available. So, in the case where the system essentially goes between being completely coherent to the state where it essentially is being possible to be seen after a certain period of time, is the sort of like the ideal versus the real cases, and many a times these are therefore measured in terms of the density matrices, because the advantage of looking at density matrices is that the property of the system can be captured very well there. And so, this is one of the areas where a lot of efforts have been put, especially in terms of ensemble systems like NMR, or in many coupled spin systems where these studies have to be done in a very coupled studies manner. One of the important aspects which we have been always talking about is the idea of entanglement, which gave rise to the age-old aspect of the Einstein-Podolsky-Rosen's paradox, which simply deals with the fact that measurement of one essentially leads to the measurement of the other in terms of an entangled pair. Essentially, it means that before you measure that the spin could have been in either direction. However, whenever you measure the spins, they are always anti-correlated, entangled in a way that is impossible if the spin values existed before the measurement. And this is a weirdness that was not liked by Einstein, and that is why he made this statement, and was of the impression that quantum mechanics is essentially having some flaw, because this kind of a action at a distance should not be possible to be figured out instantaneously, because if the pair is created at some point of time and they are being separated out, in spite of howsoever far they are separated out, any measurement of one of the possible states would give rise to the automatic measure or knowledge of the other state, and that is one of the issues which became a problem. We know that part of that was addressed and sufficiently correctly addressed by Bell's inequality proof, which led to the fact that it is indeed possible to do these measurements, and that has led to the entire idea of important measurement concepts in quantum information theory. So, one of the other important parts of the quantum information is the scaling, and in terms of the scaling aspects, it is important to realize that classically information is stored in a bit register. So, for example, a 3-bit register can store one number from 0 to 7. However, quantum mechanically a register of 3 entangled qubits can store all these numbers, which all the numbers simultaneously in a superposition, which is 8 numbers, because it is 2 to the power 3. And so, register of 3 numbers can essentially in quantum mechanics have all the numbers stored at the same time, whereas in classical sense it was only one number which could have been stored. So, that is the extreme benefit of the scaling that is available due to quantum information. So, as a result, a classical computer therefore is a n-bit number crunching machine, whereas a quantum computer is 2 to the power n all possible n-bit number crunching machine. So, as a result, a 300 qubit register can simultaneously store more combinations than there are particles in the universe, and that is a very important aspect of the quantum computing. So, problems in both cryptography and physics benefit from this exponential scaling, enabling solutions of otherwise insoluble problems. So, that is one of the biggest advantage of the quantum problem. Weinberg, who got the Nobel Prize for cold atoms, also shown. Wineland at NIST, who also got the Nobel Prize for cold atom discovery, has shown metrology applications of cold atom based ion trap quantum computing, and that he was able to show because of the usage of the entangled atoms, which gave the benefit of producing large array of states together simultaneously, and the nature of uncertainty of prime concern in accurate measurements typically. And so for n classical independent atoms, they are randomly, or they can be oriented in a certain way in a in particular set. However, for n entangled atoms, it can be shown that the short noise limit is possible with a larger accuracy. And so these are of heavy applications in metrology also, and so this was one of the additional benefits which was shown by Wineland group. So the idea of quantum mechanics merging with information science has led to the revolution of quantum information science, which is a big advantage. In the simplest possible state of the atomic qubit, the idea of the use of spin states of the electron can be simply understood from the fact that it is its rotation one way versus the other can be correlated to the way the overall spin of the electron is going to affect because of its connectivity with the nuclear spin, which is of one way or the other. So the lower energy state would have a condition when the spin of the electron is opposite to that of the nucleus, whereas if they are of the same kind, then it will have a higher energy state. So any particular case, an atom can be either in 1 or 0, but it can also be in the superposition possible state of the two cases. So atom light interaction in the trap can be utilized to use atoms for quantum computing or quantum information processing. So the counter processing laser beams can create a standing wave where the periodic light shift potential is equivalent to the optical lattice, and the light shift can be utilized to make sure the photon scattering or the decoherence is so small that it can be utilized for getting very long lived trapped atoms, which can be used for quantum information processing. So this optical lattice holds manipulates atom by light shifting, and these are going to be very useful to create the standing wave periodic light shift potentials where the particles can, the atoms can essentially lie. So the periodic potential of an optical lattice is a natural nanoscale register for atomic qubit. Typically speaking, when we talk about ion traps and ions, magnetic field and others can be utilized because of the charged nature of the system. However, for the atomic case, it is only the spin which is being utilized in this case, and so the idea of light producing a optical lattice for which the interactions can be set up with the atoms is very effective. So in such a case, lattice can be set up as small as say 400 nanometer spacing, and that can be addressed with light, and so a Bose-Einstein condensate can thus be loaded into a lattice of this sort. A huge number of atoms in the lowest state in a magnetic trap can be easily generated in a Bose-Einstein condensate, and such a Bose-Einstein condensate can then be put into an optical lattice, as which has been produced by a standing wave created by counter propagating light, and the way to then address these atomic states have a way to these lattice states of these atoms being addressed by either using the adiabatic process, where all the Bose-Einstein condensate is in the lowest state. So it is an adiabatically cooled condition, or it is a adiabatic turn on condition. It could be non-adiabatic, where the superposition of excised states are also involved, and that is how the states could be put together, and those loaded states can then be looked at by suddenly non-adiabatically releasing the atoms from the lattice projects the lattice wave function into the free space. The periodic wave function has momentum components at multiples of the reciprocal lattice momentum, which is twice the photon momentum, and this is the same as diffraction, and as a result this can be measuring how this system behaves, and as a result this can end up helping in terms of working with the atoms as if it is in a crystal lattice. So, here is the way how the system can essentially be looked at in time. So, in temporal evolution of the loaded 1D lattice can be seen that under adiabatic condition everything is lowest possible state, whereas when adiabatic conditions are applied so that it suddenly is provided with an impulse and it can undergo or have excited states coupled with it and can give rise to other aspects. The adiabatic loading can put the atoms in about 99.5% of the ground states, and this is the kind of work which Wineland was able to show, and was highly appreciated in terms of the work that could be done with this case. It also need to be understood that in this case each site needs to be just one atom. So, the initialization of say 10 to the power 5 qubits in a 3D lattice greater than that is necessary. So, these Bose-Einstein condensate is then which is being addressed by light would have to be looked at in a slightly different way, and this is the kind of work which has been reported in this work by Wineland in 2003, wherein it was possible to make the lattice have a adiabatically deepened criteria by making the field change the frequency, going from change the property as it made it deeper versus shallower, and the lattice is deepened adiabatically. Adiabatically means it is done slowly, the ramping is done so that the deepened adiabatically repulsive interactions arrange the atoms one per side, and that is how it was possible to set it up in such a way, and it was shown to work not only from his lab in NIST Boulder, but also it was shown from the results in Munich, Max Planck. And so, according to theory, ground state provides a very high fidelity of initialization of a massive register of neutral atoms, qubits at certain voltage values, with an error rate of less than 5% chance of any of the 10 to the power 5 sites having an error. So, that is the level of fidelity which was possible to be achieved by using this adiabatic principle of making sure that the atoms are loaded in the sites of interest. The next process essentially required the application of quantum processing of a single bit operation, which could be simply done by using Raman transitions between, because there are two laser beams anyway which are there to provide the lattice. So, the two laser beams can induce transitions between the atomic cubic states, and that could be utilized for the quantum processing. And however, the problem in this particular case lies in the fact that the atoms in the adjacent lattice sites are not optically resolved, because the beam, the laser beam, even though it is tightly focused, it would hit more than one atom, because the diffraction limited spot size of a laser cannot be better than the wavelength of light, roughly in that range, and whereas these lattice sizes are going to be much better, could be smaller in terms of their arrangements. And so, what their demand was that they wanted to have tightly confined atoms far enough apart to resolve with a laser. Otherwise, tightly focused lasers would still hit more than one atom, and this one of the approaches that Weinberg's group made was to use a super lattice of local atoms with every nth lattice atom, where the property of the light was used in such a way that they were able to utilize this. These are more details of the exact experimental parts, but it is important to realize that they were able to use atoms for doing quantum processing, an area which we have always alluded to, but we did not really go into the details, and so I thought show you certain details of this problem. They were able to do a pattern loading of the system in Gettysburg, these 2002 experiments of theirs, and these spatially pattern loaded atoms were being addressed and studied by using light as a means to do the computational aspects, in this case the quantum processing. So, they were able to show 2 qubit operations by using 2-bit neutral atom universal gates by entangling atomic states through coherent atom collisions, and in this particular simpler approach they use the Sirach-Zoller gate, in which state selective movement of atoms and ground state on site interactions between atoms were utilized for accomplishing entanglement. So, the preliminary results on the controlled coherent phase shift in these kinds of experiments enabled the motion of the atoms. In this sense, they are sort of similar to what was shown in terms of the ion trap studies that I had discussed in detail earlier. However, here it is important to realize these are atoms, so they are not charged species. So, it is not the magnetic field which is used in these cases. These are all optical fields which are being applied in very controlled fashion, so that these kinds of motions can be available. So, this was one of the aspects of the atom trapping principle which was used for showing quantum computing. So, this is similar to the idea in terms of ion traps. However, here an optical lattice is being used to load the atoms and individually address by use of principle of coherent atom-atom collision between the states by using laser beams of appropriate wavelengths and energy, so that they can essentially do this kind of a activity. So, in some sense this kind of work was quite unique in relation to the ion trap also, although it followed similar principles. And with that I am going to end the aspects of looking at the ion trap and related aspects of the quantum processing, which in this case we specifically focused a little bit more on the atom traps to also include this idea, as has been quite obvious in our previous discussions. And we will be carrying forward the discussions into the other some aspects of solid state quantum computing that we looked at earlier into the next lectures. So, see you next time.